Hello everyone, I'm going to talk about our paper called SCADA Data-Driven Wind Turbine Main Bearing Fault Prognosis based on one-class supervector machines. This paper is created by my partners Vidal, Tutivén, and me, Insuasty. Okay, who am I? My full name is Germán Andrés Insuasty. I'm an electronic engineer from Universidad de Nariño. Right now, I'm a master's degree candidate in electronic engineer. I live in a south of city in Colombia called Pasto. My main research topic is about machine learning, multispectral image, anomaly detection, and object recognition. If you want to know more about me or my work, please visit my webpage andresinsuasty.com to see more details. Let's go to see our agenda. First, we are going to see about the introduction, after failures, description, methodology, results, and conclusions. So, in the introduction, one of the important characteristics of renewable energies is the support to mitigate the effects of climate change. It is known that there are fewer fossil fuels at every moment. On the other hand, in order to help renewable energies, it is vital to lower costs. That is the reason that this work proposes a fault prognosis methodology to predict the main bearing fault several months in advance. Imagine that to know maybe a failure in months in the future is cheaper than to make a corrective maintenance. Here we have an approach of one wind turbine that we use here in this study. Here you can see the components and the features that is inside of this wind turbine. And if you want, you can see here the more features or characteristics like nominal power, that is 2,300 kilowatts. The rotor diameter is 101 meters. It's a little big wind turbine. That this is to know that it's a real wind turbine that is studied here in this work. Continue to the failure description. The bearing damage and failure can be classified in different ways and use different terminology. You can see here the classification of these failures like fatigue, wear, corrosion, electrical erosion, plastic deformation, fracture, and cracking. Continue with the methodology. This image can show you a very simple way of our technique. First of all, we extract information from SCADA data. After this information is processed by an algorithm trained to identify anomalies and depends on what characteristics parameters the classification is anomaly or normal sample. This triggers an alarm to prevent those types of failures. This is achieved by using only SCADA data, which is not created for this purpose. The data is accessible on all industrial-sized wind turbines. Thus, this methodology could be applied to any wind turbine with very low added cost, since the necessary sensors are already installed. Let's talk about our data SCADA. We have a lot of data since January 1 from 2014 to December 12 to 2019. This is a lot of data recorded by every 10 minutes. And we split this data in two parts. The first one is the training data, that is inside of this training data is only healthy behavior, is a normal behavior. And in the test data exists two types of behaviors. One is a normal data, but another is a failure data or failure behavior, because on June 11 from 2018, exists a report of failure in the main beer. So our methodology explains that we use only the trained data to identify how is the normal behavior, the healthy behavior, and with this information, this algorithm is used to extend this process to identify a failure in the test data and identify also the normal data, the normal behavior. We use two types of variables. The first one is the wind speed, and the second variable is a combination of the shaft temperature and ambient temperature. It's important to note that we use a normalization in these variables to be more efficient in the execution of this algorithm. If we can see in a graphic wave this data, you can see here these graphs represent in blue tones the training data and green tones the test data. Here we have the two variables used. Above we have the temperature and below the wind velocity with this split of the data. The blue the training and the green the testing. With the data in our mind, how we use this data to train an algorithm? Okay, so the algorithm used here is one class supervector machine that consists in minimization of a function subject to a restriction. This minimization is optimized with every training sample that we have in our training data set. And after we make this optimization, we use a decision function to classify every sample like a normal sample or an anomaly sample. The output of our algorithm is a classification in normal or an anomaly sample. This classification is grouped by month, and we count the amount of anomaly sample classified. So in this example, you can see here for the month 1, we have an amount of anomaly samples classified, and the month 2 is bigger than the month 1. And we established a threshold that means that every month is less than the threshold is classified like a healthy or normal behavior, and the months that the amount of the anomaly detection, the anomaly reported is bigger than the threshold, it represents an alarm to be reported. So let's go to see our results. Please have in mind that we use a split of our data, and now we are going to see our test data that inside it has a failure behavior and a normal behavior. And here you can see our results. We have all this test data classified with normal sample or anomaly sample, and we count the number of anomaly sample by month since December 2017 to December 2019. The failure that is reported in this real wind turbine is in June of 2018. And you can see here the amount of anomaly reports in this month. And we established a threshold to identify this failure. This threshold is established by the average of anomaly, the reports of anomaly with at least 3 standard deviation above. That is the reason we established this threshold around 1,000 samples classified like anomaly per month. And you can see here that in April of 2018, the alarm is triggered because the anomaly reports is bigger than the threshold. And the conclusions we have that in this work, a fault prognosis methodology to predict the main bearing fault is stated. It is based only on SCADA data and needs only healthy data to be trained. Other conclusion that is that the proposed methodology works under different and varying operating and environment conditions. And the third condition is the methodology is demonstrated on a real underproduction wind turbine. The results show that the alarm is triggered months before the fault appears, thus giving time to the plant operator to schedule maintenance. And thanks, I hope it has been of your interest. Thank you very much. See you.